Hello everyone, I'm Diego. I'm from Brazil and I work as a software engineer at Variscite. I'm here today to present this webinar where I'm going to discuss embedded machine learning applications targeting the i.MX 8 processor from NXP. So if you are new on that, if you are planning to have some project related to machine learning, I think this might be a good idea for you. Just a little disclaimer before we get started. We have examples for pretty much all the things we are going to discuss. It is in our GitHub, so please check the webinar description after watching this webinar. So let's get started. This is our agenda. First of all, we're going to briefly talk about artificial intelligence, machine learning. Then we will jump to the processor, which is the 8M plus processor from NXP. Then we're going to talk about model quantization, YOC to BSP, our own API, and some other important concepts like warm-up, profiling, and that's it. Well, now I'm going to discuss what is artificial intelligence, just to give you a briefly overview. Artificial intelligence, it's pretty much just applying intelligence to machines. And what we are going to discuss here is the machine learning. Machine learning is a subfield of artificial intelligence where we can train data and we can create a model. So it's different from other types of computer science algorithms like OpenCV that has hard-coded rules. On machine learning, we can train a model with a data set, and the algorithms from the deep learning that we use on machine learning will generate a model for us, which will recognize the patterns for us. So instead of having a hard-coded rule for detecting some object, we have algorithms from deep learning that can recognize the patterns for us and create a model. And that's what we use it here. So we have artificial intelligence, which is applying intelligence to machines. Have machine learning, which is a subfield, which learn from experience, which learn from data. And we have deep learning, which is pretty much the heavy algorithms that we use to train models, right? So let me jump a little. So this is basically how machine learning works. This is the flow. We have basically two steps. One step we do on your computer and the other one we do on the embedded device. On our computer, we need to train a model. So we collect data. We can collect several pictures of anything we wanted. And we use an algorithm from the deep learning. It can be from some framework like TensorFlow, Keras, PyTorch, whatever we want, as long as we knows what we want, in fact. So we collect data, we train the model, and we test the model. So the step we do on our computer or in a cloud server is to create a machine learning model to detect what we want. And then we deploy this model into the embedded device. And on the embedded device, once we have the model, we need to create an application. And this application will get a new input from a camera, from a file, and it will pass through the model and get a prediction. And this process of getting a new input and passing through the model and get a prediction, this is called inference. So just to have an idea, this is a little different than using hard-coded rules like OpenCV or anything else. So let's move forward. Where we can use machine learning applications, we can use to detect it, to recognize objects, images. We can use in voice recognition, in anomaly detection, in smart wearables, in factories, in medical centers, and plenty of other places. We have some advantage of having machine learning on the edge instead of having on the cloud server. And I think one of the most important ones is the bandwidth, because neural networks requires lots of processing, because sometimes it has a very large amount of data. And one of the penalties of transferring this over the internet is the latency. And we also have security. Decentralization, it's a good one, because instead of having a remote large system which consumes a lot of power, we can use on the embedded device with less hungry and less vulnerable attacks. We can have more power efficient as well. The cost, which is a low cost system. Availability, sometimes we create an application to run at somewhere which has no internet connection. Customization, we can customize a neural network for your application and pretty much fits your needs. Redundance, and those are the topics I think it is important for us to have machine learning on the edge. So now we are going to talk about the i.MX 810 Plus processor from NXP. Well, I think most of you knows all these features, but this model in specific has a different thing from all the others. It has the AI ML NPU acceleration, which is an engine core which can run up to 2.3 tera operations per second. The NPU is for us to use when running inference. So this is the most important thing for us here. And beside that, we have all the other features which help us a lot with the applications. The Cortex A53, HDMI, the GPU, audio, Bluetooth, USB, and pretty much all the other things. Here I just highlight in the i.MX 810 Plus what is important for machine learning, what we can use it. Of course, we don't have any examples with Cortex M7 in this slide, in this presentation, neither with the ISP. We are just going to use the neural processing unit, which is the NPU, and also the Cortex H53. So those are the features which are important to us, but we are only going to discuss this time the neural processing unit and also the Cortex A53. Here I just made a comparison for you to understand a little more how the NPU is way faster to run inference and how we can get some advantage with that. On the left side, we have the most powerful processor for NXP, which is the i.MX. And on the right side, we have the 810 Plus. So here we have two models. The green one is the classification model, a model that just classifies the image. And the blue one is the detection one, which can detect the objects in the image and draw a box around the object. So we can see the times. We can see on the i.MX for just one A72 core, and also for all the cores, and also on the GPU. And on the right side, we have one core for the M+, which is the A53. We have all cores, the 4 cores for the A53 on the M+ as well. We have the GPU on the M+, and we have the NPU. The NPU can run the classification model less than 3 milliseconds, and the detection one less than 12 milliseconds, which is very good, which can help us to have way more FPS in a video, for instance. So I think this is just a graphic, but I included in this slide a GIF which I recorded on the M+, so you can see the difference. On the right side, we have the same model On the both sides, we have the same model, but on the left side, the red box, we have the CPU, which runs the inference more than 200 milliseconds, which is not good because we can get less than 10 FPS per second, and that's not good, right? Um, on the green box, we have the NPU running the same thing, the same model, the same input size, and the inference time is just 12 milliseconds, which we can get frames per second around 25, 30, which is way more nice. Uh, we can run the video way faster, So as we can see here. Um, Here is just a slide where we can have an idea where we should use the NPU. So we have the Cortex M7, the A53, and the GPU. And for small things, we can use into the GPU, which is 1 operations per second. But more than that, like speech accents, interpretation, scene segmentation, gesture, it uses way more than 1 operations per second. And that's the point where the NPU comes in. So if you are planning to create an application, keep that in mind because we can use all the cores to run inference, but sometimes it requires lots of processing depending on the application itself, and then we need to use other cores. And the NPU is prepared to work with way more operations per second. Now we're going to talk about model quantization benchmark. And this is very important. If you decided on your project to use the NPU, you must have in mind that NPU only deals with 8-bit fixed point operations. It doesn't deal with 32-bit floating point. Of course, it will work, but it will be very slow, the inference time, which will increase the time, and we will get less frames per second in a video, for instance. So we need to use a model which is quantized. And the method for that, we have two. We have the QET and we have the P2Q. The QET you do over training. So if you are training a model to detect fruits or cars or any other object you want, we need to training to transform the weights and bias from 32-bit to 8-bit fixed point and during the training. And the other method is the post-training quantization, which we do after training. So we just train a regular model, and then we convert the model to 8-bit. So with that, we need to keep in mind that the model will be reduced by 4 times, and we will probably have a faster model, but we can also lose some accuracy in the model. This is not an easy step. This is the most trickiest part in machine learning, I think, at least for running on the NPU. And if you can, of course, buy a model, you can use an open source model, but if you are going to customize your own model, that's one thing you should do it. You need to quantize your model to 8-bit fixed point. And once you have your model, if you want to know how your model will behave on the i.MX 8M Plus processor, we have a tool inside of the BSP, which is the benchmark model, where you can run your model on the CPU, the GPU, and the NPU core. And that's the way you do it. And you can see here that I'm running for a default model that comes with our BSP, which is the MobileNet. And we can see that the NPU is way faster than all the other cores. And On this slide, I just got a MNIST model, which is for handwritten digits, which is very small model, with a very simple network. And we can see that the CPU, it's way better than the GPU and the NPU, because there are cases where the inference process is faster in the CPU core because of the parallel execution and also the model size that we are using. The NPU still cannot deal with parallel executions. So there is no good answer for that. As I said in the beginning, we need to do, we need to study, we need to understand what we need for our own application and decide which core we are going to use it. For models, for neural networks, for applications that requires lots of processing, of course, the NPU is way better than the CPU. But for the smallest ones like the MNIST, the CPU is better. So we need really to understand our needs and develop it on top of all these things that I'm discussing. Now we're going to talk about the Yocto BSP, and pretty much everything that NXP includes in their default BSP, which comes from the AIQ, we also have it here in Variscite with a little extra things that I'm going to discuss in the next slides. So NXP includes in their default BSP PyTorch, OpenCV, TensorFlow Lite, i.MX, and everything that NXP included, we also included by default in your current BSP. So you just need to go to our wiki. You just need to build in a Yocto BSP, and you are good to go to use all the things from the AIQ from the NXP. And this is the extra thing I told you about it. Here in our site, we decided to go a little further, and we create some examples to help the customer, to help the developer to get started with machine learning. So we have our own API, which we call it PyVar. And PyVar, it's written on top of an XPAQ software development environment, which is the one I just talked about it. It's free, anyone can use it, customize it. PyVar comes with several examples demonstrate the full power of the NPU, the CPU, the GPU. We have some advantage with PyVar. We don't need to use any cross-compile, fetch images, or make deployments, reading extensive guides. It's very easy for you to add, to reuse classes, add new features according to your needs. It's very easy to install. Also, you have the BSP from our wiki. You can just run a command and you are good to go. If you want to learn more about PyVar, you can just access pyvar.variscite.com, and we have several examples to help you in your development. Here is just how we install PyVar. As I told you, we just need to have the latest BSP. And we just need to run pip tool install PyVar, and you're good to go. You just need to follow the instructions in the pyvar.variscite.com, and we have several examples, which I'm going to show right now. You just need to boot your board, install the PyVar package, and for instance, let's run object detection using i.MX. You just download the source code and you just run the example. It will open the camera, it will run the inference for you, and you see on real time how machine learning works. We have several examples to help you with that. You can use the source code, you can modify, it's totally free. It's just to help you in your development. And there is one more thing that I need to talk about this. Since NXP includes several frameworks, i.MX is one of that, and i.MX is the only one that we can choose the core. where we are going to run the inference. With TensorFlow Lite, we cannot do that, not with the Python bindings. We can only do that if you run, if you rerun the application using C++. So, but you know, in the examples with the RMNN, you can see the difference. Of course, probably you are not going to use that, but it's just here for you to understand, for you to learn. So if you can modify, just go to this line and change accelerate to false. And then it will run on CPU and you see the results and you can compare and see what is best for you. And here are some important concepts like warm-up and profiling. Warm-up was previously talked, showed in the previous slides, but I decided to talk it in here only because sometimes we can be a wrong impression when we run the inference on the NPU. Because if we run the inference on the NPU, we just for one picture, we will have the impression that it is lower than running on the CPU. That's because we need to do some overall initialization steps for the NPU. But once it's all loaded, the next frame and forward will be very accelerated. So it's just the first time. So that is a way to improve that, which we can export to variables, which are in the slides. But this is just for you to keep in mind, for you don't think that NPU is slower. NPU is not slower. Just like this GPU, we need to perform some initializations first. And the other thing is the profiling. If you have any trouble with your model, if you don't get it, what is happening, you can export some variables in your user level, and you can see very detailed what is loading, what is going to the memory, and everything. So everything that is hiding from you, you can see it with this variable. You just need to copy it and export it. It's all set it in your BSP already. Here are some useful articles that I really think if you are interested in machine learning, you should do it. You should read it and try it. We have this getting started with machine learning, which explain pretty much what I have told you. We have the PyVar, which I highly recommend you to use as well for learning. We have some source codes. We have several source codes actually that you can use. It's for free. We just did it for your needs, to help you. We also have the links for the NXP where you can learn more about that, and also the user guide for machine learning from NXP. If you have any questions, you can go to the Variscite.com, send us an email, check in the Variscite wiki or GitHub. You can create a request on our GitHub or anything you want, anything you prefer. Thank you. This is a very briefly webinar, just to show the important things from machine learning. Everything you need will be in the webinar descriptions, all the link. It's very detailed, and we have several examples that can help you to develop your own application. Thank you for watching, and that's it.